All right, I'm going to provide an assist with the problems that follow, but I want you to try them on your own using the information we've taken down in our notes. And once you've done that, circle back to me and ask questions. So, important for us, we're looking at cross sections perpendicular to the x-axis. So that means we're talking about with respect to x. We've got two functions here. All right, we've got this guy, which is a sine curve, right? This is sine pi x. Oops. Notice we do have an inside there, that pi x. So if we're integrating sine pi x, we are going to have to use substitution. And then our other curve here that forms that area, this bottom one, is going to be x cubed minus 4x. So our bottom curve is g of x. So this is our lower. And our pink guy up there is our upper. All right, so what I'm going to do now is give you the equations from the notes for each of these and talk a little bit about what we've have going on. So I'll kind of draw us a cross section to imagine, and then you'll follow through and try each of these problems. So we've got our equilateral triangle here. All right, so that height, remember, was equal to root 3 over 2. I'm sorry, root 3 over 4. Come on, erase. No, that's right, root 3 over 2. The difference between our curves. And this bottom piece here, our base, was the difference between our curves. All right. So you have the equation for this integral to find the volume, but if you don't feel like flipping back, this is what we have for our equation. All right, so go ahead and try this problem, but let's go ahead, keep going and look at our cross sections here. So next one says semicircular cross sections. So our cross section for the entire base, which is our diameter, would be f of x minus g of x. So you need to bear in mind we're talking about our radius to find that volume, right? And our volume for this guy is pi over 8, the integral from a to b, the difference between our curves. Then we have isosceles right triangles. So for those, our base is the difference between the curves, and our height is the same because it's an isosceles triangle. So when we found our volume, we had half integral from a to b of f of x minus g of x squared with respect to x. And then lastly, for our, well, not lastly, second to lastly, our sides, which are congruent for squares, were both the difference between the curves. So this one, the volume is equal to our side squared, f of x minus g of x, with all of those individual areas of the cross sections being added together. So that's what the integral is telling us. And then this last one, we're considering the relationship between the height and the base. So my base is still going to be f of x minus g of x. All right, but my height, my height is going to be some constant a times that base length. So when we say the cross sections of rectangles have a height that's twice the length of the base, a is going to be 2. Our volume equation for that was a times the integral. Oh, that's unfortunate. I should have used a different variable here, shouldn't I? So it's a constant, so it doesn't matter which variable you use. I'm just going to call it, it's a variable we don't normally use. Don't normally use e. No, that's not good. Let's call it z. All right, so I don't want you to think that the constant and the bound a are the same, because they're not. So if it's double the length of the base, the height, then it would be 2. If it's 20 times the length of the base, then our height would be 20 for that z. All right. So go ahead and try these problems and reach out if you have questions.